Yeah, it's an absolute delight to be here. A lot of the stuff that I'm working on is building on things that are going on here, so I'm really delighted to sort of bring it back to the original audience. Okay, so the original task that got all of this started was dealing with a problem of modeling tumor phylogeny over time. And rather, we had gene assays every few months for different patients, and they were all irregularly sampled through time. What I'm showing you up here is the timestamps of different observations in an ICU data set, where patients are in the ICU for 48 hours, and all sorts of different measurements like blood pressure and temperature are being taken at all sorts of random times. And we would obviously like to model this kind of data. I think the sort of the vast dark matter of problems are in like business and health, where all data is kind of like this. We just don't talk about it very much because it's really awkward to deal with. And I would say that most of the big parametric models in machine learning that we like to use to model time series are fundamentally designed for discrete time, like recurrent neural networks, or even the deep Markov models. We could, of course, project to discrete time by binning, but of course, then we have to average entries per bin or leave them empty, or we could do imputation, which is, I think, weird because you kind of have to solve the original problem, the same problem you're trying to solve, which is modeling the data in order to impute it, and then you permanently mess up all your uncertainty estimates. Okay. So I still think the best place to start looking for ways to deal with this problem is latent variable models. In particular, my favorite family of latent variable models today is the deep Markov model, where we specify with some neural network the transition probability of some latent state. This is like, Z is like the true hidden state of our patient or our business or whatever that we're trying to model through time. We model how that state changes in some time invariant way. We also have to learn this likelihood, the emission probability that says how likely are we to see different kinds of data at different times. One thing I want to point out about these deep Markov models in comparison to normal autoregressive models like recurrent neural networks is that all they do is define a joint distribution over the latents Z and the observations X. If we want to compute the marginal likelihood of the data P of X, we need to integrate over Z. We'll also need to integrate over Z if we want to make any sort of predictions, answer all these different queries that this model supports. But one point I want to make is that we can integrate out Z however we want. And according to my definition of models, that doesn't actually change the model. That's just your approximate inference strategy. You can do variational inference, MCMC. You could do some sort of weird quadrature strategy. Whatever you want, that's just up to you. You can change your strategy for integrating out Z at any point. In practice, we happen to also use some big neural network to consume all of our X's and combine them in some, let's not say ad hoc way, but let's say some complicated, not necessarily important way, and output a distribution, a joint distribution over Z's to parameterize some approximate posterior P of Z given X. If we're doing variational inference, then it doesn't matter what form we make P of Z given X, or rather, let's call it Q of Z given X, except that the closer we are to the true posterior, the better our inferences will be. So again, I want to say this is only here to speed things up. After we trained our model, we could do any sort of approximate inference. This is just learning to recognize different situations based on data we've seen before. Okay, so any question about this so far? All right. So how do we extend this sort of model to continuous time? Well, obviously one set of tools that is sort of custom made for this setting is ODES, where we have, again, a vector valued state of our system, but now we're going to say it changes continuously in time according to some function that we're going to specify. And so every function or probability distribution in this talk, I'm going to say can be parameterized by a neural network or whatever you want, and we can always fit this by stochastic gradient descent as long as we can compute our marginal likelihoods. That's just sort of like taken for granted. And of course, when we want to make predictions using this model, we end up having an ODE initial value problem where we have to say, if I started at this point in this vector field, where would I go if I followed it locally? There are many different approximation strategies, the oldest and simplest of which being Euler's method that takes sort of discrete steps along the way, each accumulating error in an uncontrolled way. And of course, due to 40 years of excellent work in the numerics field, we also have sophisticated adaptive solvers that can, control the error explicitly and have sophisticated extrapolation strategies such that they don't need to take tiny steps in order to navigate these vector fields when the dynamics are, sufficiently simple. Okay, So the first stab that me and my group took at dealing with irregularly sampled data by having continuous time models was this ODE latent variable model. And the basic idea here, for those of you not familiar with graphical model notation, is that this circle means that z at some time 0 is a random variable. We're uncertain about it. Then we specify f, the dynamics of this latent state, and we can use some ODE solver to deterministically evaluate what the entire future trajectory of this, let's say, patient is, or rather the entire trajectory of their latent state. And so these diamond nodes mean that these are deterministically determined by the z at time 0. Once we've computed this entire trajectory, all of the observations we might make are conditionally independent. So it's easy to compute likelihoods. That'll just end up being a product of all the likelihoods of the different data we saw conditioned on the data, or rather the latent state at that time. So I realize that I'm rushing, but this is kind of the point that I think we can stop and breathe and make sure that everyone's on the same page about what notation I'm using, what I even mean by latent variable model. Does anyone have any questions about how does it actually work? How do we actually train this model? You know, what's actually going on? I don't want to lose anyone at this point. Yes?
How do you have some just way that you're modeling the distribution of z dt0,
Yeah.
and then you're transforming it by this kind of nonlinear transformation given element. Do you have a representation of what the probability of dpm looks like as a random variable?
That's a good question. Yeah, so the question is, well, if we have z t0 and a distribution over it, and f, what's the distribution over z of ti, or something like that? Well, conditioned on z of t0, it's just a delta. It's a deterministic thing. If this is, say, we're still uncertain about it, then yes, we will imply a distribution over z of ti. And we actually can compute the density of that model as well. So that's something that we talked about in the original neural ODES paper, is that there's a nice continuous time version of the change of variables formula, this like instantaneous change of variables formula. It's kind of like a special case of Fokker-Planck that lets you actually figure out how the density evolves according to the ODE as well. Yeah. Okay, any other questions?
So for your ODE solve process,
Mm-hmm.
since dt1 to dtn are all random variables, if this process handles the randomness?
So the question is, does this process handle randomness in ZT1s? So no, conditioned on ZT0, everything is deterministic. So, and I think you guys should already be saying, well, this is obviously not going to be the end of the road because this is a silly model, right? We don't usually think of modeling someone's physiology as being completely determined at birth by like their genes or whatever. One thing I should mention is that these P of x given ZT, that could be any sort of likelihood, not just a Gaussian likelihood, but maybe a text model or something like that. To train this model, all we need is that we can differentiate this likelihood with respect to Z and its parameters theta. Okay. So I mentioned before that something that's not part of the model, but something that we need to do inference in the model is the recognition network. And so in this particular model, we need to somehow consume all the x's that appeared. So this might not be clear, but this is our data set, these x's at different times. I'm just kind of reflecting it over here to talk about this process of consuming the data to output a distribution over of Z0. Right? The only variable that we need to do inference about in this model is Z0. So we need to consume all the data, whatever times it might come at, and produce, in this particular case, Gaussian with some mean and covariance that depends on the data we've seen. So I'm not actually proud of this thing. It's just a kludge that is a neural network that is capable of taking in data at different times and does a reasonable job. You can sort of do whatever you want here. This is accidental complexity, an engineering detail. But when we're training, we need, the training loop looks like take a data set, encode it, do importance sampling from this proposal distribution, compute some lower bound on the marginal likelihood, and then take gradients through all of that to maximize the likelihood of our data according to our parameters. Okay, any more questions? The audience is always right, so really, please don't be shy. Okay, So this is what training one of these models looks like on a synthetic, just toy data that we can see what's going on. So the green dots are some data points. And these purple lines represent posterior samples from, we condition on the data, sample Z0, run the ODE forward in time. And after training, it fits the data pretty well. This little whirlpool down here, that's showing F, or rather a two-dimensional slice of F. Our latent dimension here, I think, is 4 dimensions, and we're just showing a two-dimensional slice of it. So this is what the neural network is learning. And then once we've trained this model, we've implicitly defined a prior on functions that we can sample from by first sampling from Z0, which is just some Gaussian, it's not really important, and running our ODE solver forward. Okay, so this model works pretty well when we're actually modeling deterministic systems. So as a toy example, we said, oh, let's take the Mujoku physics simulator and take a little hopper guy, start him at a random position, and then just let the dynamics happen. And one nice thing about these latent variable models is that the latent state is a sort of meaningful quantity, at least according to our model, in a way that the hidden state of a recurrent neural network is, I would say, not. So the point of this slide is, so what's happening in this video is that this guy starts in the middle of the space, he falls down and hits his butt. And so he had a large change in momentum right around here. And if we look at the dynamics of our latent state at this point, we can see that definitely something happened here. Whereas if we model this data with just a recurrent neural network, the hidden state of that recurrent neural network is kind of a weird conflation of, well, it's a funny vector-valued representation of a posterior. It's not really clear exactly what it means, but it's just sort of randomly spiking. We don't expect it to make sense, and it doesn't. This is just a point in favor of latent variable models in general. Okay, any more questions? Yeah, so this works really well on a truly deterministic system. Let's go back to the system we actually wanted to deal with, this ICU data set. Yeah, so we were able to do better than sort of standard RNN-based models. We tried the RNN GRUD from David Sontag, which also worked pretty well. Yeah, I would say, this is a pretty good model. One kind of disappointment from me was that this Poisson model didn't do better, and I want to explain what that is very briefly. So one thing that I think that's missing from most time series models is a model of the time of arrival of different observations. And of course, when the data is regularly sampled, this doesn't add anything. But in a situation like healthcare records, the fact that the patient showed up at the doctor's office in the first place already tells you a lot about what's going on with them, probably. So there's been some models like Hawk's processes that kind of try to evaluate this likelihood when they have very simple rate functions. The rate is the relative probability of seeing an observation. But we have typically only used simple rate functions because you need to be able to compute their integral across time in order to evaluate the likelihood of a Poisson process. So one nice consequence of being able to differentiate through ODE solutions, which is something that has been known for decades, but we just added to PyTorch last year, is that now we can also evaluate Poisson process likelihoods and not just model all the data we have conditioned on it arriving at a certain time, but jointly model the probability of something being seen at a particular time and what the measurement is. And so here you can see our inferred rates for different measurement types on a certain patient in the data set. And okay, it makes sense that there's a lot of measurements around the time that the rate is high, right? It's just a sanity check. Okay, so far we tried to deal with continuous time by going to this ODE model, and it sort of works. But it's really weird to have these deterministic dynamics. And as we make our time series longer that we're trying to model, we have to stick more and more information into this initial condition. And it's like really weird to think that if someone gets hit by a car when they're 20, it was somehow like foretold by their initial condition. Like that just doesn't make sense. It's also a weird inference problem because we have to see data about the person when they're at a certain point in time, go back and ask what does that tell us about their initial condition, combine that with all the data, and then make predictions forward in time as well. And it's just weird to have a special time t0, right? Like that's just unnatural. Okay. So let's be more like the deep Markov model. So these probabilistic transitions, you can also sort of think of as z of t plus 1 is z of t plus some noise. right? And this noise is what's going to let us deal with all these weird things like people being hit by cars or all the little weird interactions that happen throughout life that we don't have the capacity to model in our huge Markov deterministic state. One nice thing about this kind of generative model, if you're familiar with graphical models, is that if I were to, let's say, here's Z1, here's Z2, and I have data at these points, if I've observed this data, if I said, oh, actually, no, there's another variable in my model, and there's some data, but I didn't observe it, what's the probability of this model? Sorry, forget that I added this guy, but if I were to add some extra observations to any model and then not observe them, by the fact that probability is normalized to 1, you can just remove them from the model without changing the answer of any question. So, you could say, well, it actually wouldn't hurt us to add extra time steps in between the observations in this deep Markov model. It would still be the same model. So let's see what happens when we take the infinitesimal limit of adding more and more state transitions. So the infinitesimal limit of this, I would say the only reasonable answer is to get the classical definition of a stochastic differential equation. So this part is a little bit hand-wavy, but the idea is that we had this ODE, and we want to somehow add noise, right, like in parentheses, or in quotation marks. It turns out that the sort of only nice way to do this, and that lets you coherently reason about sort of taking smaller and smaller steps, is to imagine this noise as coming from differences in a Brownian motion. So, if I imagine having a little bit of different noise at each time, I would end up with a sort of white noise process where everything's uncorrelated. The integral of this white noise process is a Brownian motion. I can go back to white noise by just asking what is the sort of change in the Brownian motion between any 2 points in a sort of self-consistent way. So that's why there's this kind of slightly unnatural construction. So the formulation we're going to be working with here is that there's a deterministic part of our dynamics, and then a part that gets multiplied by random noise. And both this f and this sigma, again, they're just whatever functions we want them to be. We can parameterize them by neural networks or whatever. OK, any questions about the setup so far? All right, so let's turn this into an actual model. So one thing I want to mention is, this SDE, might seem weird that we have this Brownian motion. It might seem like a very specific way of modeling things, but I'd say it's actually a very general way of modeling things. In particular, it's a natural fit for when there are many tiny unobserved interactions in a system that we just don't have the brain power to model directly. So, the original Brownian motion was from motion of molecules in a fluid being hit by all sorts of millions of little particles. Population geneticists use this to model allele frequencies in a gene pool, where every time animals mate, the probability of, or the relative frequency of that allele goes up in the gene pool. Trades cause prices to change in the market a little bit each time. And the nice thing is that these interactions don't need to be Gaussian, right? Like an allele, when an animal has kids, its allele frequency just goes up by a discrete amount. But we get the Brownian motion because the central limit theorem kicks in. So actually a whole bunch of different processes, when we take the infinitesimal limit, give us these Brownian motion style SDEs. I want to say that, the question?
I just want to know, should we be thinking about it just as a scalar, or is this going to be a general matrix?
That's a great question. So in general, Z is going to be a vector. F is going to be sort of size of that vector to size of that vector. This Brownian motion can also be a vector of a totally different size. And then this sigma can be a matrix in general. Yeah. Okay. It's kind of funny. This SDE only really applies in this intermediate regime when there's enough interactions such that things look Gaussian, but not so many that they completely smooth out and the variance goes to 0, right? Like at some point you get like an ideal gas law and you don't need an SDE anymore. And if you only have 10 animals in a system, you again shouldn't use an SDE. One thing I'm afraid I'm going to forget to say it later. So we're going to use this in a latent variable model. So I think we'll have a lot more flexibility than you might expect to use this particular type of noise to soak up whatever sort of, whatever remains to be modeled by our dynamics. Okay, so what I'm going to propose, the whole point of this talk is Oh, yes?
Is there theory on kind of what is the general class of random processes that this kind of Brownian motion SDE can describe? Like, is it as flexible as any of our discrete time random models?
That's a great question, actually. I've never actually thought about it in comparing it to discrete time models. I will say that, we're going to come back to this at the end, like there are Gaussian processes that you can't model with this, like white noise is a Gaussian process that can't be modeled by an SDE. SDEs are definitely, I think, intuitively a bigger model class than GPs just because we can, we can model all sorts of non-Gaussian marginals and joint distributions with this sort of SDE. So actually, that's a central question that I think this talk should address. I'll have to say, I only started learning about SDEs like a year ago. I don't have a great intuition or examples where I would say, this is something that you definitely cannot model with like Gaussian processes or something like that. Okay. So the point of this talk is saying, let's put some neural networks into these functions here and learn them to model all sorts of time series that has all sorts of funny randomness and irregular time samples and everything. Okay. So I also want to say, I'm not the first person to start thinking about this. And I realize this is a cheesy meme. This is something that someone else made, and I couldn't resist putting it in the talk. So obviously, last year we had this paper, Neural Ordinary Differential Equations, which is like interesting title. I chose the hypey title. Anyway. And now I'm punished for it by in the next year, these 3 different papers came out that all were neural stochastic differential equations of some sort, right? It's an obvious generalization, an obvious next step. I was actually pretty sure, actually David Sontag asked me at NIPS saying, oh, are you working on SDEs? And I said, yes. I was pretty sure that someone else who knew more about SDEs than me was going to do it first. And so this first paper, Neural SDEs, Deep Latent Gaussian Models in the Diffusion Limit, made this point that a deep latent variable model where you add noise at each step does correspond to an SDE in the infinitesimal limit, and you can maybe do some sort of variational inference in this model. And they showed how to do forward mode autodiff in this framework. So that is how to trace the SDE solution forward and compute gradients with respect to parameters along the way. The problem is that that doesn't scale. You have to do a separate forward pass for every single parameter in your model. So they used it to train like 5 or 10 parameters. The Pellecci and Favaro paper worked out that an infinitely deep convnet with uncertainty in the weights in every layer also becomes an SDE. And then this Gia and Benson paper, it's not actually an SDE. They took this latent ODE model that we were playing with and then said, let's add finitely many jumps. I should draw that. Yeah, instead of having just deterministic dynamics, we can have jumps at some unknown times. And then the problem is that we have to integrate over when and how big these jumps are. And it's just a slightly awkward inference problem because integrating over this like joint discrete continuous space, I'd say, is hard. So part of the motivation for this neural SDE is we have to put some randomness in. Let's just put it in that into the solver so that we get our dynamics and our inference for free together. Okay, any questions about related work? Or anyone who feels like slighted, I should have mentioned them right now. There's actually a lot more related work. I'm just covering the papers that actually have the word neural SDE in the title. Oh, yes. So there is also an awesome set of SDE solvers that you can differentiate through implemented by Chris Rukakis. So yes, good point. Okay. So there's this question of how do we fit these parameters. I'm saying the existing methods are sort of unsuitable. And so how should we fit them? Well, I'm going to say let's generalize what we did for the ODE setting. And what did we do for the ODE setting? Well, yeah, the task is we have some ODE that we've defined and some loss, which in this case is a marginal likelihood, but it could be whatever you want, some regression accuracy. We need to compute the gradient of this scalar loss with respect to this huge vector of parameters, and maybe there's a million parameters. So one thing we could do that Chris Rukakis does all the time, and it, I would say, works on, well, there's different scaling properties of different ways of doing things, which is to backpropagate through the operations of the solver that you use. So these solvers are just a bunch of linear algebra and if statements and stuff. There's no reason why we can't just write this in PyTorch or Julia and autodiff through the whole thing. And the main limitation there is that you either have to do forward mode, which doesn't scale very well with the number of parameters, or you have to do reverse mode, which requires you to store the intermediate quantities, which then has high memory costs as you have large models in long time series. I would also say, it's kind of a subtle point that the ODE solvers are trying to control the error of the trajectory of the state. They're not trying to control the error of the gradient. If you control the error of the state perfectly, I think you'll get pretty good estimates of the error of the gradient, but it's just not something that's being directly controlled. And Alexei Radul over at Google always says you should approximate to the exact derivative, not differentiate through the approximation. But this whole thing is kind of like, there's been religious wars in the numerics communities about these two approaches. I'm not going to say this is like the only way to do it. It turns out that it's pretty, well, in retrospect, it's pretty straightforward to derive the continuous time analog of backpropagation. So these are the update rules for if I have sort of like Euler integration of a ODE or like a residual network or something like that. I have to ask, how does the loss depend, or how does every layer depend on its input, and how does every layer depend on the parameters, and then just chain all these Jacobians together. And then, Pontryagin was writing a long time ago about how, yeah, this actually leads to another set of differential equations. We already have these ODE solvers sitting around. Why don't we just use AutoDiff to compute all these Jacobians, or Jacobian vector products, rather. We already can do that. And then put this whole thing together into another call to an ODE solver here that will run backwards from the solution to compute all the gradients that we need to update our model. Okay, so any questions about this? Okay, wait, all right, awesome. One really cool thing about this is that, as I was mentioning, backprop through the solver is memory intensive. If you do this backwards solving trick, you get constant memory gradients, which is even better than training a neural network, right? So the cool thing about one cool property that ODEs have that most even neural networks don't have is that you can run their dynamics backwards. So the idea is that AutoDiff normally needs to store all the hidden activations. We can just run the dynamics backwards to recreate them as we need it on the fly. And of course, this does introduce extra numerical error, but at least there's an ODE solver that's trying to control that error. So, and it's so easy to write the backwards dynamics. They're just the negative of the forward dynamics with negative time, and you start at negative t1 and go back to negative t0. Okay, any questions about this trick? Cool. So obviously, I'm an academic. I want to just use the same trick again to get another paper out. So why don't I just say, if SDE is just like an ODE with noise, why don't I just apply the adjoint method? So the first main obstacle is that you need to store the noise. Like the idea is that on the forward pass, I needed to call my random number generator a whole bunch of times to get this random sequence of like Gaussians that determined my path. And I need to use the same randomness on the reverse pass in order to get unbiased gradients. And it's kind of funny because I guess I'd say in machine learning, there's this idea of the reparameterization trick for building gradient estimators, which is that you should take all the noise in your model, sort of factor it out into parameterless, fixed, like uniform or Gaussian noise that has no parameters. And then once you do that, you can treat everything else as just like a deterministic computation condition on this noise. It's kind of funny. SDEs already sort of do this. They take all the noise in the model and put it into this Brownian motion that has no parameters. Anyway, so what we need to do is somehow sample an entire function and store it for later and be able to query it wherever we want without using like too much memory. So we figured out this trick, and then we found out that it's like a well-known thing. It's like pretty simple. There's this algorithm called the Brownian Tree that says you can actually sample from a Brownian motion with arbitrary accuracy at any point without storing anything more than a single random seed. And the basic idea is that there is this thing called a Brownian bridge, which just says if I have a Brownian motion that I know the two endpoints of, I can compute the mean and variance of that Gaussian at any point in between. It's just like kind of, linearly interpolates. And if I just say, okay, well, I know the Brownian bridge at the beginning, and now I need to find this sample at this point, I'll sample in the middle. That'll give me another Brownian bridge that's half the size. Sample in the middle of that. That'll give me another Brownian bridge. And I just keep sampling finer and finer Brownian bridges until I've found I'm like within epsilon of the point that I'm interested in finding. So this has like a really nice recursive definition. It's like one of these algorithms from the book, The point is that for a cost of like to get within epsilon of the location that I wanted to sample, I have to pay only log 1 over epsilon steps to get there. So we have to pay a little bit more computationally to sample in this way compared to just sampling a single Gaussian, but it's only sort of a factor of log of 1 over the epsilon. Okay, any questions about this trick? Yes? Where am I sampling? So in this example, we only went a little bit down the tree, but we're trying to sample sort of somewhere around the bottom of that black line. Oh, so while we're solving, usually we start at the left, and we sort of go along like little bit by little bit. If we're running adaptive solvers, sometimes we need to sort of go back and forth a little bit around the same point. I don't know if I can say anything in general about how far they need to go. I'll just say if we have a fixed step size solver, we'll definitely go that fixed step every single time. Maybe I don't understand your question. Oh, sure, you could bound it if you want. I mean, I think that would be a fine way to construct one of these samplers, or one of these adaptive algorithms. I guess it's not clear when you chain a whole bunch of these bounds together if there would be anything left. That's a good point. I don't want to talk about it anymore right now, though. So, okay. Okay, so the second problem is we have to somehow like run the SDE backwards. And to me, it's like, well, that's fine. I sampled some Brownian motion. I integrated it from left to right with some other dynamics. I should surely be able to integrate it back from right to left. And so I said, okay, well, yeah, let's just slap some negative signs on all the dynamics, and it should be fine, right? And of course, to my credit, I was knew enough about SDEs by then to realize that I should do this in the Stratonovich formulation, which is there's two different ways of formalizing SDEs. There's like very easy to transform between them. One of them says sample the noise first, then take a step. The other one says like take a half step, add noise, then take another half step. The second one is like time reversible, and that's what physicists use. So if you, so yeah, you should definitely do this reversal, this trick in the Stratonovich parameterization. But Zhoichen, he just finished his undergrad, he's a Google resident who really is the one who did all the work on this paper, and Leonard, who's the probabilist who I collaborated with, they both sort of, their hair went white, and they're like, what does that even mean? Run an SDE backwards. You've adapted this sample to a filtration, and then you're going to adapt it to another filtration backwards? Like, that's just a type error. It doesn't even make sense. And, much later, they sort of said, okay, well, actually, if you view it in this other way, it's fine. And then they spent a long time proving that it makes sense, that there exists a sense in which it's meaningful to define this reverse flow that does reconstruct, in a strong sense, the trajectory that you found on the forward pass. So our draft right now, the whole middle section of it is 4 pages of proofs of yes, it's actually okay to run this SDE backwards. And actually, some of the results are based on this new book by Kunita, who's one of the sort of pioneers of ODEs. He's pretty old now. He finally released another book, and that actually helped us crack this one. So, okay. Any questions about this? Yes? Mm-hmm. The question is this log 1 over epsilon cost, do you pay it on the forward pass? Oh, so you have to pay it on the forward pass and the reverse pass. There might be a way to do it without having to pay it on the forward pass, but it wouldn't really change the asymptotic complexity. So, yeah. Any other questions? Okay. Yeah, and there's this adjoint dynamics that I showed you for the Pontryagin stuff. It's it's what you would guess it would be for. It's you just sort of do the same thing for the noise. I know this looks like a big mess, but it's just sort of one call to a vector Jacobian product, which is what AutoDiff does for you automatically. So we can automatically get the reverse dynamics and the gradient dynamics for free automatically from any AutoDiff library. Okay, so now we have this new algorithm that we say has O1 memory costs and O. So remember I said that we had log of 1 over epsilon cost? Well, if I have so L is the number of steps in the solver, and so then the size of the steps, if we have a unit interval, would be it would be C over, C over L. So, and we actually needed to pay a log of, negative log of C over L, which is log of L per step, so it's L log L. And actually, that part is really fast. That's just like sampling Gaussians. Evaluating the dynamics is the expensive part, and we only have to do that once per step. So this is really like worst case.
What was C again?
Oh, that's just the size of the interval that I'm integrating from T1 to T0. That's like the size that like epsilon will be this. Sorry. Yeah. Hi.
Is the representation of the model coming from, is that also, you mentioned earlier that the Brownian motion would be a matrix, for example, and I imagine that you mentioned it more simple as well.
Sort of. I mean, I've normalized all of these in terms of evaluations of the dynamics of the system. So we sort of normalized that out here. Yep. OK. So this is great. Now we have this. So for the neural ODES paper, we took a 50-year-old algorithm and just put it into PyTorch. But then, surprisingly, there wasn't actually this stochastic adjoint, like the version for SDE, so we had to do it ourselves. So we did it. Now let's fit these SDE paths to data. So actually, that's not quite it. And this part also, like all the other people working on this realized this too, which is that if I just fit a SDE to data, sorry, this is just like math in case I was afraid that there might not be a good Blackboard. I'm just going to like go through this more slowly over here. So first of all, if we just try to fit some random process to data directly, it's going to ignore the noise. Like if I have some data here and enough parameters in my SDE, optimizing for maximum likelihood will just, at the beginning there'll be tons of different noise, and it'll learn to make the sigma be 0 and just always hit the data every time. It's like if I fit a Gaussian to a single data point, the optimal Gaussian has no noise. It just like sits right on that data point. What we actually need to do is define a prior over functions and then somehow condition on the data to get a posterior over functions. This is like the right thing to do. It's like what we do when we use Gaussian processes, for instance. And it just so happens that we have a new way to define distributions on functions, which is through SDEs. But we define them in a really implicit way, right? When you write down a Gaussian process, you're saying exactly how to evaluate the probability of a particular function at a finite number of points. But we're going to say, we're going to use these SDE to implicitly, we're just going to say how to sample from this prior on functions, right? So Z is f of z, some theta. Right, and then those crummy diagrams up there are supposed to represent that I don't actually know the density of this thing in function space. I just know that if I have a fixed starting point, I can sample one of these, call it an SDE solver, and then get some complicated paths. And that implicitly defines a distribution over functions. OK, so now what about when I want to condition on data? Right, I have to say, well, I have to before I even know how to like do inference, I at least have to parameterize my answer. So we'll say that our approximate posterior and I don't really know a great notation for this. I'll call this like ZQ, because it's the same Z, it's just a different sort of description of it. OK. You might think this is a typo, that this theta appeared here. I'll get to that later. So now we have these functions that specify our prior over functions. And that's kind of like when we fit a Gaussian process, we have the kernel hyperparameters that say what is the prior over functions. And then we're also going to have these parameters phi that specify our approximate posterior over functions. So the remaining question is, well, how do we fit the marginal likelihood, right? We want to know what is P of x given, let's say, theta. Well, it turns out that there's this nice lower bound. So this is the standard variational lower bound that says, OK, Q of z given x. This is just like any distribution. Okay, so there's lots of different ways to write the lower bound. Like this kind of represents in expectation the KL divergence between the prior and the posterior. Yeah. Oh, thank you. Yes. Oh yeah, great. Yes. Cool. Okay, so this is one of the ways to write the standard evidence lower bound that is tight when Q. We want, it's an equality when Q of Z given X equals P of Z given X. And just to remind you what I mean by Z and X, here Z is like an entire function draw over like some huge domain. X is all the data that we might have seen, like all their medical records or whatever. So this log P of X, that represents all those little arrows, hanging off my latent thing, saying what the probability of the data is given my latent thing. Okay. So the cool thing that, again, we did not invent, and like Maxime Rodzinski knew about way before we did, is that it turns out that you can write this thing as integral of all right, I hope I got that right. dt. Yep. So marginally, this kind of looks like the formula for the KL between two Gaussians. It says, like, if the means are different, that's bad. And then the whole thing is scaled by the variance. And you can sort of think about this, that if I have some field F, like that's saying I should be going down, and some small variance, like in the prior, I definitely don't want to be facing the wrong direction, and especially not when the prior variance is like really small. This is like a very sloppy cartoon, but just to give you a feeling for like what kind of things this KL likes. Okay, so any questions about this elbow? Yes?
So this relies on the fact that the data are the same.
Yes. Yeah. And so another obvious central question to this whole thing is, what do we lose by making the sigmas be the same? And I actually don't have a great answer for that yet. We just sort of worked this out like a month ago. So yeah, if anyone knows, I would love to know. Okay. Does anyone know? Okay, I'm sorry. So the cool thing is that, so this is an expectation over something we can sample from, right? We know how to sample from Q. That's just run the SDE solver forward. And we can compute this and compute that. So we can use simple Monte Carlo to optimize this elbow by gradient descent, which is where we want to be. So I'll say this is cool. This is not like, we didn't invent this model class, but this is a model class that now you can optimize for very long time series with huge latent states and millions of parameters. Well, I'll say in principle, so far we've got it up to 10,000 parameters. But again, we just got all the code working like 2 weeks ago. And I'd say it's kind of like an alternative to something like Gaussian processes. And I still don't yet have a great characterization for what you can do with this versus not. And we'll talk about that more in a bit. But it's very flexible. You can define any likelihoods here that you can differentiate with respect to Z and train everything together with gradient descent, which is where we like to be. Okay, and then one thing I want to come back to later is like, if we have a diagonal matrix here, everything works out, and sort of half of the work of this paper was like noticing that everything like just barely cancels out, so you can use this Milstein scheme without having to compute the V areas, which is like an annoying thing that happens when there's like cross terms. So it feels like the math was saying you guys should use diagonal noise here. It's going to be great. Yes. Yes.
I thought this whole diversion was about how to drive the elbow for maximizing lower bound likelihood. Like, first of all, was that like,
Yeah.
how did that address the first one?
So what I mean is you can't maximize the sort of likelihood of X. Let's see, how do I say that? Yeah, what am I trying to say?
I think the first one is saying that,
I see. No.
you don't want you could easily overfit.
Yeah, so if we just maximize the likelihood, we're maximizing P of X given Z without incorporating the prior term on F, or on Z. Yeah. So just to be clear, what he's asking about is, I'm saying don't maximize P of, so don't maximize expectation over Z of P of X given Z. Maximize the expectation over Z of P of X comma Z. That's what we're doing now. We're incorporating the prior. Yeah. Good question. Cool. So now we got through the math. Now we get the results. So this was just generated 2 nights ago by Joy Chen. So here we're using an Ullstein-Umbeck prior, which is a Gaussian process prior, because some SDEs are Gaussian processes, but Laplace likelihoods, which means that the true posterior is non-Gaussian. And now this is us using stochastic gradient descent to fit all the parameters of our Q, like our approximate posterior. And it fits it, and it does what you think, and the data is irregularly sampled. So, ta-da. And then here's another example where we have like a slightly different gap in the data, and it, I think no one could say for sure that this wasn't a GP if you just looked at it, right? But again, we all just barely got this working. This is like super work in progress. But I promised scalability. So here's us fitting a data, again, neural SDE to a series of trajectories of motion capture data, 50-dimensional. So the data is like the location of all these little points on someone's body through time. 6-dimensional latent space. We fit neural networks with 11,000 parameters to this, and it beat all this sort of other continuous time models on this set. And I'm really sad. This dynamics looks really floaty. Joy Chen said it looks less floaty than if you look at the sample from the other guys yet. I haven't seen it yet, so it's like secondhand. But the point is, I would claim before this, like it would be hard to fit this many parameters on this like even medium-sized model. And we really strongly suspect that we should be able to scale this up to millions of parameters, just like any other giant deep model. Okay, so now the hype portion of the talk is over. Now the lowering expectations. So one thing is, SDEs are kind of an awkward world to live in, and the ODE solvers that we have are like much more mature, and they tend to have like higher order convergence. And in general, like Chris knows more about this than I do, but the convergence order of SDEs that scales much worse with the number of function evaluations that you need to do in general. Would you say that's fair? Yeah. Yeah. So we're always going to find it slower to solve SDEs, sort of asymptotically than ODEs. And then, as I mentioned, everything we're doing, we're making this have diagonal noise, what that means is that sigma I, so this sort of outputs like a diagonal matrix with all zeros, and along the diagonal, sigma I only depends on sort of Zi. So it's like element-wise sort of noise. And I would say that that's probably not a serious limitation because this is all happening in a latent space. But I don't really have a great feeling for how much of a limitation this is. We don't need it. We can do whatever we want, but then we have to compute these Levy areas, and that's painful. I don't really have a feeling for how painful, though. Very painful. OK. And then, as I was saying before, what if the patient gets hit by a car? It's maybe not very natural to model that by he just had a very bad series of seconds in his life that all kind of added up to like a bad minute. I think it's like, no, they just had one very bad second. OK. Yeah, I wanted to come back to this. I don't really have a great feeling for what things you can express with this sort of model versus GPs. One thing I'll say is that the inference in this for time series is great compared to GPs, right? Like there are ways to turn GPs into state space models. Here we start with a state space model, so we know there's no cubic blow up anywhere. And another thing I'll say is that it's clearly very natural for me to model like an intervention where I have some patient's trajectory, and then I give them a drug or an injection or a shock, and then I think that their state changed a lot in that second. I can definitely do that in this framework very easily. I don't really know how to do that in a GP framework. OK, so I think, yeah, right on time. Oh, yeah, I want to say one really cool thing that I'm excited about with this model class is that imagine I'm a doctor, and I measure a patient's heartbeat on an EKG. It's like a baby, and I don't see them for a month. And you ask me, what's their heartbeat going to be like a month from now? So a long time from now. I'll say, oh, they're going to be bigger, so the period's going to be lower. It's going to be more like this. If I wanted to try to model that with like one of these dynamics models, to answer questions about the patient's heartbeat a month later would require me to actually run trajectories out an entire month. However, in an SDE model, if I set things up so that my approximate posterior mixes back to the prior away from the data, then I can say, oh, there's like some mixing time like tau, and I don't know exactly what happens here, but within 10 seconds, I'm like back to the prior on heartbeats. So I know that the KL divergence between my prior and posterior will be 0. So I can just skip all of this whole month and then just sort of like fade in right before you asked me. And I can give you a coherent posterior over heartbeats a month from now without ever having to do all this inference in between. And I think this is going to really pay off for like multi-scale models where you have to reason about like solving a Rubik's Cube and then like, walk over a desert and then like solve another Rubik's Cube without ever like tracking the details in the interim. Okay, there is this connection to infinitely deep Bayesian neural networks, which I think we don't have time for today. And I guess I'll say, right now we're working on the code base. Chris has done a lot of work on this as well, and I invite any of you guys to collaborate with us on trying to get this to be a usable model. Okay, thank you very much. And I want to point out, Joy-Chan Lee is applying for grad school next year. Leonard said it to me after Joy-Chan left the room one time. He's like, man, it's like working like with a postdoc. And I totally agree. He read the whole literature. He knows more about SDEs than I do. He wrote all the code. If he applies to your group, you should take him. Okay, thank you very much. The end.